Alright, welcome. In this video I'm going to walk you through calculating the deflection angle and the distance. So this is what we'll be looking for right there for this station of 120. So I'll go through it and I'll check it as I go. And I'm going to bring the calculator here. Alright, so we have to calculate the length, which is real simple, because so first of all, from station point of intersection, it's not called the station, it's called the point of intersection, to station 42.60 plus 42.265. That is the distance from here to here. All right, I'm going to change the color. So we'll see what's given. This is, and the only reason why I'm doing this is because in one of the LSIT exams, they didn't give you the typical drawing. It was something like this, and you have to know that's the interior angle, or delta. And so that's kind of the reason why I'm doing this. It just didn't look like the stuff I'd seen typically in the class to learn it. So hopefully this helps you understand what may come up on the test. So station from PI to the point of beginning of curve BC will be the distance here, right? So 100 minus that gives you the station here, BC. And then end of curve is the length of this, right? So it's not 100 plus this tangent, it's the length of the curve. So you add and then since it's provided, you can just do the subtraction, right? What I did here, 1.46, so 146.985 minus 42.265, and that gives us the length of this curve. And let's see if I did something like this, and then hit the dimension arc. I wonder which one it's going to pick. 104.72. So that's the length, and it's called a capital L. It's not that's the differentiation. A horizontal curve, this is L, and in a parabolic curve, the vertical curve alignments, the horizontal line is called L, I think, or LC they'll call it sometimes. But so you can calculate easily. You can calculate the length of this arc. And let me go back. I want to keep that point because it's already dialed in. And let's see, so we have the length. Now we're looking for the arc. We know station 120, so you're going to go 120 minus this will give you the length of the curve from 120 to the point of beginning of the BC, the beginning of curve. And we'll do 120. Here you go, 1 plus 20, station 120. Length to station 120 is equal to 120 minus the 42. So that'll give you the length of the curve in between those 2 points. And that's what you need to use for the calculation. It comes out to 77.735. And then you're going to divide that by the length of the arc, the total length. And then you're going to multiply that by 30 degrees, not 60, it's half. And then because if you don't do it, it gives you the angle from the origin of the circle to here, but it's up here on the deflection angle, it's half. So that's how you get that. So the deflection angle is right there, and we can copy that. Control C, V, J, enter, and then hit that, paste that there. And then you go off this, and it'll intersect that at that point, right where that intersects. So we'll do that. That's what we're looking for, is that angle here, Alt and A. All right, and then, so that angle there now if we go from here, so we got the deflection angle. Now we're looking for the origin, right? The distance, right? So you have to calculate this length here so that we can do some more information. We're going to need, we're going to need the radius, right? So the radius is 57. That's so what we have is that we have the tangent and we have the angle. We know this is out to MA. It's going to be 30, right? So we have the tangent here, which is like the rise, and we need the run, right? The radius. So we're going to go 57 over x is equal to the tangent of 30, and then you're just going to solve for x and you end up with 100. So now we have the radius. And now that we have the radius, we're just looking for this triangle here. Let's get rid of this. And we know this angle, here's the deflection angle for that. This is going to be double, so the half of this is the same angle as that, right? So V, Control K, Alt MA, we know that angle. It's the same as that, right? So now that we have the diagonal, we're looking for this x. We're going to double that x, and that'll give us this distance here, right? So we're looking for 75.792, and that's what we got in the calculation. So if you go x over 100, so half the distance here is x over 100 is equal to the sine of 22.2694, and then you solve for x, and that's what it looks like, and then you get your distance of 37, you multiply that by 2. You know, in the formula you're going to see 2 times sine of the deflection angle times the radius, right? But I'm just showing you where it how it breaks down geometrically there. And then you get your distance and your deflection angle. That's pretty much it. It's really important to understand. And it's kind of weird because I forgot. I mean, I just assumed the deflection front and back, and then I ended up with 2 different stations that one didn't work. And anyways, I kind of forgot. So I'm reviewing this for myself. And you know, I mean, typically you're going to go into total station, you're just going to put in the coordinates, and you're going to backside and foresight to your points. And this is designed for a theodolite. So if you don't have distance measurement values in your theodolite, you can't really shoot coordinates so easily, right? It's easier to do this than to calculate the coordinates for the individual points, and it's more reliable. And that's it. Hope that helps you in your career. Probably going to help you mostly in school, but thanks for watching. Have a great day.